Okay, yeah.
Okay, so should
Just
I
hold on.
continue?
It's being screened in YouTube live also because there are a lot of people. So
Yeah, so should I wait then?
just a minute. Let me.
Okay, okay, sure.
So it will work now, I think.
Okay. Start.
Okay. Yeah, so after giving a detail about the our decomposition protocol, then we will go to the conclusion and what are the like outlook from this project and what can we do more from this. Okay, so first an introduction about an NP center in diamond. First of all, why is it diamond? Like there could be some other semiconducting material, but what is so special about diamond? First of all, the diamond has a large band gap, which is around 5.4 eV, which keeps its conduction band mostly vacant. So there is no interaction of electrons with the vacancy electrons. Secondly, for performing experiments at room temperature, it is important that there is a very less interaction of the spins of the defect center with phonons, and with diamond it's possible. So in diamond there is a very less interaction of phonons with the vacancy electrons at room temperature, which makes it possible to implement many quantum protocols at room temperature using NV centers and other defect centers. Secondly, even the naturally abundant diamond has very less magnetic impurity. Now there have been lots of advancement in going ultra pure diamond samples. So basically, it's like really possible to have very pure diamond samples where the NV centers can be embedded. So the NV centers will have less interaction with the magnetic impurities. So the NV centers can be considered as isolated quantum system. Now, there are many possible color centers possible in diamond. NV center is like one of them, but there are some other defect centers possible, like the group 4 elements also can create defect center in diamond. For example, silicon vacancy, germanium, tin and lead vacancies, which have also got a great deal of attention recently. But so far, NV centers are the ones which have been exploited mostly in terms of having their applications in quantum information processing, quantum sensing, and quantum communication, and so on. So what is an NV center? It's basically a nitrogen atom which replaces a carbon atom, and then it gets coupled with a vacancy, which is the nearest neighboring vacancy, and then they form a composite system which we call a nitrogen vacancy center system. So now from nitrogen there are 5 valence electrons. 3 of them make covalent bond with the 3 carbon atoms, nearby 3 carbon atoms, and 2 creates a lone pair. And in the vacancy there are 3 electrons come from the 3 carbon atoms nearby, and out of these 3 electrons, 2 form a quasi-covalent bond, and the third one remains as unpaired. So this is the electronic structure of the what is called a neutral nitrogen vacancy center in diamond. Now when it accepts one more electron, it becomes a negatively charged nitrogen vacancy center in diamond, and that is the one which is mostly exploited so far. Now let's have a look what is the electronic level structure looks like. So this is the electronic level structure for a negatively charged or NV minus center. So here there is a spin 1 electron, and in absence of any magnetic field, the ground state is split into 2 levels, 0 and the plus minus 1, which are the degenerate levels. And then there is a energy difference between this 0 and plus minus as 2.88 gigahertz, which is the 0-fold splitting. And in the excited state, it's the same, but the 0-fold splitting is different, which is 1.42 gigahertz. So now it can be optically addressed. So it has a large band of excitation range, but it's usual to excite the NV centers with green light, which is of around 532 nanometer. That's the most common one, which is around 2.33 electron volt. So with this much of energy, the system is excited from the ground state above the excited state to a virtual absorption state. And from that state, it comes down to the excited state non-radiatively. And but during this process, the spin is always consumed. So if it was excited from the ground state at ms is equal to 0 state, it ends up in the ms is equal to 0 state of the excited state. Now from the excited state, there are certain transitions which have certain probabilities. From the excited state ms is equal to 0 state, it can decay to the ground state ms is equal to 0 state. It's the same for the ms is equal to plus minus 1 state. Now there is also a high probability that if the system is in ms is equal to plus minus state at the excited state, it decays to the ground state ms is equal to 0 state through two metastable states. This has a strong probability. It also happens in the other way. From ms is equal to 0 of excited state, it can come down to ms is equal to plus minus state in the ground state, but that has weak probability. So now this decay path from ms is equal to plus minus 1 to ms is equal to 0 in the ground state has a non-radiative transition. But since this decay has a strong probability, it allows us to initialize the system to the ms is equal to 0 state. So when we keep on exciting the system with optical pulses for longer time, there is more and more population which basically comes down to the ms is equal to 0 state. So this is an advantage of having this non-radiative pathway. So now, so far we are talking about only optical excitation. Now let's include the microwave excitation. Let's include a microwave excitation which is transition selective between the 0 and plus minus 1 state in the ground state. Then what happens? Then after initializing, let's say we are illuminating the light in a longer time scale. So we have a significant amount of population in the 0 state, ms is equal to 0 state. But then when there is a microwave which is transition selective between 0 and plus minus 1, it excites a significant amount of population to ms is equal to plus minus state in the ground state. And then it takes the non-radiative pathway to decay down to ms is equal to 0 state. So basically when we apply a microwave which is transition selective between these two levels, we see a decay in the fluorescence. And that is called the optically detected magnetic resonance. Now these are degenerate states. Now if we apply a magnetic field that lifts the degeneracy of the ms is equal to plus minus 1 state, then we have instead of one level, two levels, and those two levels have different energy spacing with the ms is equal to 0 state. So instead of then one dip in the fluorescence, if we sweep the microwave frequency, we will see two dips. So this the frequency spacing between these two dips basically signifies the Zeeman splitting between the ms is equal to plus minus 1 levels. Now the same thing happens in the excited state. So when one sweeps the frequency, one can see these dips in the spectrum, both in the excited and the ground state as it is shown in this picture. And these are all, so now we are talking about the NV minus center. So under, when you sweep the wavelength, the optical, basically the wavelength, then we have a spectrum of NV centers with this red curve. And in the similar way, depending on the NV0 energy structure, we can have a different spectrum for the NV as the blue curve. Okay, so another advantage of NV center is that it emits single photon. So this makes it a very suitable candidate for applications in quantum communication and quantum optics, because it is a very stable single photon source. Basically reported these results. I will show it later. So how is it done? It's basically done by measuring second order autocorrelation function. So using a Hanbury, Brown and Twist interferometer, using a start-stop histogram, the coincidence is measured, and that tells whether we have a single photon at the input of this beam splitter or not. So when the signal, the single photon signal from the NV center enters the beam splitter, it's splitted into two paths. And then if it's a single photon, then both the detector cannot click at the same time because it's single photon. So what is done? From the signal from one detector is used as the start, and then the other detector. So it's basically it. Whenever there is a signal in one detector, it registers that event and then wait for a stop signal from the other side. So, and then whenever it detects another signal from the other side, it registers that event and it counts it as a coincident count. Now, when the path difference, when we change the delay, then we see that for a certain amount of delay, there is no coincidence or there is no event detected. So this delay corresponds to the optical combined with the electrical path difference between these two paths. And if they are having the exactly the same and optical and electrical path difference, then there's at zero delay we should get a dip. So that signifies that at the input we are basically giving single photon. So there are a number of fascinating properties of NV center. For example, in 2009, this was a pioneering experiment which showed a long coherence time of NV center. In this experiment, they used a conventional Hahn-Echo sequence to measure the coherence time, and they observed 1.82 millisecond of coherence time. After that, a number of experiments have been done to study the coherence time in bulk and nanodiamond using many different dynamical decoupling sequences and all. So this is one of the results from an experiment which was done much later in 2018. It was from Tim Taminow's group from Delft. And there they applied dynamical decoupling sequences for many cycles, up to 10,000 cycles, more than 10,000 cycles. And they could enhance the coherence time up to almost 1.5 second here. Okay, then as already we discussed about the single photon emitting capability of the NV center. This was the first experiment which showed that the single NV center emits single photon, and it was done also using a Hanbury, Brown and Twist interferometer, which was shown in the last slide. And then they also observed that NV center doesn't move spatially, and NV center gives single photon at the same intensity level, so it doesn't do any photo bleaching or anything. Then another great property of NV center is that an NV center can be used as an isolated quantum system in basically the diamond substrate. And these are two pioneering experiments from Michael Lukin's group, which exploited the NV center as quantum registers. So basically the electronic and nuclear spins in an NV center can be associated with a quantum register, and then certain computational tasks can be performed using that by exploiting that particular spin register. So now the NV center, as we saw in the last slide, that it has certain optically addressable states, and now the electronic levels are addressable with microwave frequency, nuclear spin levels are addressable with radio frequency. So what did they do, they basically designed a sequence of optical, microwave, and radio frequency pulses and performed the spin manipulation. Yeah, and so the first curve suggests a Rabi oscillation measurement, an example between two spin levels, and the second one is a Ramsey type free induction decay experiment between some spin levels. Now another advantage is there is a constant improvement in basically improving the reading out efficiency of the spin states from NV center, and there are already some nice techniques to do it very efficiently. So while optically reading out, what people have done, created solid immersion lenses on the diamond. So first, an NV center is located on the diamond on the diamond substrate. Then by doing a top-down fabrication method, a hemisphere is etched such that the NV center becomes at the base of the hemisphere at the center. Then when the fluorescence come from this NV center, it basically more fluorescence is confined in the solid angle than what we have got if there were no seal, if that would have been a flat surface. So this is how the collection efficiency is enhanced significantly. Also, there are ways to read out the spin charge by doing spin to charge conversion, which is shown here. All these readout techniques are actually reviewed in this nice paper. And another way of doing the readout is by reading the spin state electrically. So what do they do here? They excite the NV minus center using two photon. So it's basically two photon excitation. First it goes to the excited state, and then from excited state to the conduction band, and then they detect the signal electrically. And this technique also has been proven to be very efficient. They have been able to detect ensembles of spins up to one single NV. Okay, so now how the NV centers are prepared. So first of all, to prepare NV center, one needs to prepare the diamond. And when the diamonds are prepared, there could be some ways to incorporate or create NV centers in them. There are quite a few methods to prepare diamond crystals, but out of them, these two are the most common ones. Which one is the HPHT growth of diamonds, and another is the chemical vapor deposition. So during HPHT diamond growth, what people do, they design some kind of press and create a very high pressure inside a small chamber. Now there is an heating element. The heating element creates a very high temperature and melts some metal inside. So the heating is around 1500 degrees centigrade. Then there is the source carbon atom from which we are going to basically create the diamond. That source carbon atom dissolves using that molten metal, and then it reaches a seed diamond which is kept at the bottom of the chamber. Then around the seed, the diamond is grown. This is a very cost-effective technique, and it's very easily implementable compared to others. So this is still a common technique of growing diamonds, and there are many companies which are basically creating the diamond using this technique. So Element 6 is one of them. They sell this HPHT growth diamond substrates. Secondly is the chemical vapor deposition technique. So the main idea of this technique is using a carbon containing gauze and then use the gas carbon to make it deposited on a diamond seed layer and then create the diamond film. So generally a mixture of methane and hydrogen is used. The ratio of methane to hydrogen is typically 99:1. And then there is a heating element which ionizes the gases at very high temperature. A microwave is one way of doing it. So this is called microwave assisted chemical vapor deposition. And then there is a diamond layer substrate which is kept at the bottom, the diamond layer get deposited on the diamond substrate. This is how a single crystalline diamond is grown. And to create polycrystalline diamond, other substrate can be used like silicon or sapphire. Then the polycrystalline or microcrystalline diamonds can be grown. Now this process is performed at a very low air pressure. So if the air pressure is low, still there will be some nitrogen molecules of the air which basically gets incorporated with the diamond, and they replaces some of the carbon atoms in the diamond lattice and sits inside the diamond layer. So after the CVD growth, if an annealing is done at high temperature, what happens? There are some vacancies which are created during the growth. They become mobile, and then they start to move around and couple with these nitrogen molecules, and then they create the nitrogen vacancy centers. But in this way, there is also a high probability that the nitrogen will not get coupled to a vacancy or due to the less amount of vacancy. So generally the ratio of the nitrogen atoms which we call the P1 centers and the vacancies are 99 to 1, which is obtained during this method. But now after CVD growth, if there are many nitrogen atoms which have already replaced the carbon atoms, there should be a way to prepare the NV center from this. So for this purpose, people use ion implantation. They use high energy nitrogen ions, and those ions hit the carbon atoms and removes them. This is how the vacancies are created. Now, when there are several vacancies are created during the diamond in the diamond lattice at different positions, the annealing is performed. After annealing, when these vacancies start to move around, they couple with this nitrogen atoms, and then they create the nitrogen vacancies. So the annealing is typically done in around 700 to 800 degrees centigrade. So this ion implantation has turned to be a very efficient method because it gives a very nice spatial control over creating the NV centers to like even single NV centers at a deterministic position. They have shown this efficiency, and so this is like an example picture where the NV centers are created and arrayed from using ion implantation. There is another method which is helium ion irradiation that works more or less in the similar way like the ion implantation, that also removes the carbon atom and creates the vacancies. Then the nitrogen atoms basically get combined when it's annealed. We recently had some results of enhancing the concentration of two other vacancy centers. Those are germanium and xenon related vacancy centers. And after helium ion irradiation, when the diamond was annealed, the concentration of the defect centers was significantly improved. Now, how to measure the NV centers? So the most common technique is by using a confocal microscope, where generally a laser is used to excite the NV. The laser passes through a microscope objective. It focuses onto the diamond sample, and then the fluorescence is collected back by the microscope objective. It passes through a lens, and then it is focused at the pinhole. This pinhole is the most crucial part of the confocal setup because the pinhole gives the selectivity and it basically rejects the out of plane and the off focal signal. And also, depending on the aperture of the pinhole, the resolution of the microscope is determined. So there is some micropositioning stage. If we consider about consider the sample stage, like where the diamond sample is loaded, there is a micropositioning stage which moves the diamond in a micrometer stage. So how do we measure it? We first we change the we basically change the position of the diamond using the micro positioning stage in a longer length scale, and then we more or less focus on the area where we want to do the measurements. And then there is a nano positioning stage. The nano positioning stage scans over that area in a certain plane and then keeps on collecting the fluorescence. This is a picture of the setup we were having in ISER Pune with both the green and blue excitation. And here in the insert, you can see the microscope objective, which is basically focusing the light into the diamond sample, which is loaded in the sample holder. So how does the confocal scanning looks like? So here basically the nano positioning stage moves along x direction and create an array of the photoluminescence collected from all those spatial locations. Then it moves to the y position and then does the same. And this is how we create a matrix of the photoluminescence. And then we see where we are having the bright centers, and then we focus on them and then do the anti-bunching experiment to see whether they are emitting single photon or not. And then this is how we make it confirm that whether we are looking into a single NP or not. And then we continue with all the other experiments. So this is a typical ODMR spectrum coming from an NP center in presence of magnetic field. And then the spacing between these two dips are basically the Zeeman splitting, which was explained earlier. Now there are two charge states, and there is certain conversion mechanism involved which changes between these two charge states. This was the first paper which reported this conversion mechanism. They call the conversion from NP minus to NP0 as ionization and NP0 to NP minus as recombination. So if we start with NP minus, it basically absorbs one photon, which sends it to the excited state. Then another photon sends the electron to the conduction band. Then it turns into a NP0 state. Then, in the second step, it goes to the conduction band and it becomes an NP0 state. So from NP minus state, either it can directly come down to the ground state of the NP0, or it can go to the excited state and then decay down to NP0. Now the NP0 absorbs another photon, and from the ground state, it excited to the excited state. And then from the valence band, it collects another electron, and then it get converted into NP minus center, and it reaches the ground state of the NP minus center. This process is called the recombination mechanism, which is basically the conversion from NP0 to NP minus. So in this paper, they have shown if you keep on monitoring the fluorescence, one can actually see that the fluorescence is sometime high, sometime low. So they refer to these dark states and at NP0, and the high fluorescence state as the NP minus state. This is in all these data are from a single NP center. And now it also possible to capture the spectrum of the NP0 and NP minus. Now NP0 has a different excitation range. With blue, one can capture the NP0 signal with higher intensity than in green. So they have also showed in more details in these papers. So the ionization and recombination processes are basically dependent on many factors. I have shown some example plots here. One is the laser power. So as a function of laser power, the ionization rate change, also the recombination rate change. And then these rates are different again for different range of excitation. For example, 560 nanometer and 593 nanometer, these are different. So by formulating a rate equation model, they were able to estimate the population of the NP0 state and NP minus state. And then as a function of the laser power, they monitor how the population are evolving for these two charge state. Also, they, like I was talking in the last slide, as a function of the excitation wavelength, the ionization changes. And this is how they have got when the excitation wavelength is changed. So the thing is that there are two charge state, NV0 and NV minus, and in most of the cases, in most of the application, NV minus charge state is exploited. So we basically have to find out a way such that we can have the system, there is a high probability that the system is in the NV minus state, and it is already observed that NV0 charge state gives a flat spin independent fluorescence background, and that degrades the readout efficiency of different like experiments. For example, in sensing experiments, when for sensing experiments, it's advantageous to consider ensembles of NV center. Now, because the ensembles will have, let's say, n number of NV centers, so a number of NV centers will give n times higher signal than a single NV. Also, the ensemble of NV centers will give direction, like it will be possible to sense the magnetic field in a direction sensitive way, because the ensembles of NV centers will have NV centers with 4 possible directions. Now, having the NV0 charge state is an ensemble can degrade the readout efficiency and basically the sensing efficiency. So there should be some ways to tune the charge state conversion mechanism in such a way such that there are less NV centers in the system. So basically prioritize the NV0 to NV minus process and reduce the NV minus to NV0 process. To prioritize the NV0 to NV minus process, and yeah, also reduce the process which creates more NV0 center in the system. So to do this, one needs to have an idea that for the ensemble system, what we are working with, what is the concentration of the NV0 and NV minus centers we are having in that. So it always is useful to have a method which basically quantifies the concentration of NV0 and NV centers for the ensemble of system we are working with. So this is the motivation of our work to quantify the NV0 and NV minus concentration in an ensemble. Now we have used a magnetic field assisted decomposition technique. So it has been observed that when the magnetic field, an off-axis magnetic field is applied and its strength is varied, the ionization and recombination changes. Now this works in two different ways for single NV and for ensemble NVs. For single NV, the ionization rate changes, but it also changes the NV0 and NV minus population. But for NV ensemble, when the strength of the magnetic field increases, the ionization process changes, also the recombination process. But at the steady state, due to the ionization recombination dynamics, there is a stable population of NV0 and NV minus, and that doesn't change with the strength of the magnetic field. This is already shown in this PRB paper. So it's basically the NV0, NV minus population is not changing with field. Now, if we consider the individual system, if we consider the NV minus system, then at zero magnetic field under optical excitation, the system is initialized to MS is equal to 0 state. Now, when we are applying a magnetic field, there is a redistribution of population in all the other levels, like the MS is equal to plus and minus 1 levels, due to the change in the optical pumping process. So if there are more population in the MS is equal to plus and minus 1 level, there is a probability that those population get excited to the excited state and then comes back to the ground state through a non-radiative pathway. So with a change in with an enhancement in magnetic field, there is a decay in the fluorescence, and this redistribution of population among all the Zeeman levels, electronic spin levels, is called the spin mixing. Now, when the field is increased, the spin mixing also increases, and for a certain strength of magnetic field, we reach a completely depolarized electronic spin state, which we call the fully spin mixed state, and that corresponds to the minimum in the fluorescence. So, but for when we consider NV0 system, there is no such process happens in the NV0 system. So with the change in the strength in the magnetic field, NV0 fluorescence doesn't change. So we have used the difference field-dependent optical pumping mechanism for these two charge state as a resource to decompose the spectra for NV0 and NV minus in this work. This is the confocal setup, which I already showed. So I will just quickly go through it. We have a green laser. Then there is a lens which focuses onto an optical fiber. Then from the optical fiber, we have a divergent beam, which is collimated using a lens. And then it passes through a dichroic mirror, which reflects the green light. And then it goes through a microscope objective, which focuses the light onto the diamond sample, which on the NV centers, which we want to measure. And then the fluorescence is collected back by the same microscope objective. It transmits through the dichroic mirror. Then there is a long pass filter, which basically filters out any residual green signal. Then we use some lens to focus it into the pinhole. And then we have two different detection pathway. One is to directly see the fluorescence and use it in the confocal microscopy, and another way we just couple the signal into a optical multimode optical fiber and then do the spectroscopy. Okay, so basically what we did, we performed the spectroscopy measurement, measured the optical spectrum under green 532 continuous wave excitation and for many different applied magnetic field strength. We capture all the spectra many times, a few thousand times, and then average them to reduce the any electrical or optical noise. To make sure that the spin mixing happens significantly and we have a significant change in the NV minus fluorescence, we performed this measurement in a large range of magnetic field, such that we see a big change in the fluorescence of the NV minus center. And then we consider the field values for which we see the maximum change in the NV minus signal to do the spectral decomposition analysis. So here you can see the red curve. The green curve is the spectrum at low magnetic field. Then the red curve is the spectrum which was captured at high magnetic field, which was around 975 Gauss, and the low was around 170 Gauss. Now we write the spectrum which was captured at low field as an addition of the PL components from the NV0 and NV minus. So we have A low B as A NV0 and A NV minus. So our aim to decompose this spectrum into A NV0 and A NV minus. Now for high field, we write in the similar way, but as we saw from the earlier arguments that NV0 fluorescence doesn't change with field, we write the same amount of basically the same amount of A NV0 in the high field spectrum as well. And then when we subtract them, we get NV minus difference. And you can see in the inset that the zero phonon line for NV0 coincides for A low B and A high V. And when one is subtracted from another, we have almost flat signal. So there is no change of zero phonon line of the NV0 center when the magnetic field is changed. But we see a clear signal, clear change in the signal of NV minus signal. So now since NV difference minus doesn't have any signal from NV0, we can basically find out a scaling factor which satisfied these two equations. So by choosing a correct scaling factor, we can we can reach this A low NP minus spectrum. And then when we have this spectrum, we can just subtract that spectrum from the total spectrum, and then we can calculate the A NP0 spectrum. So while doing that, we have to make sure that A low NP minus doesn't have any signal from NP0, and A NP0 doesn't have any signal from NP minus. To do this, we performed this analysis for many different values of F, and we found the most optimized values of F to be 6.2. Now, when we reduce the value below 6.2 or we increase it, we see either a peak or dip in the NV0 spectrum at 637 nanometer, which should not happen. So we basically fix the value of F at 6.2. Now, the resultant spectra which we got from the spectral decomposition analysis are shown here. This is the blue curve, which is the NP minus spectrum, and NV0 spectrum is shown by the red curve. Now we performed this analysis for many different field values. We wanted to capture the contribution to the total spectrum from NV0 and NV minus, and then wanted to study their behavior as a function of magnetic field. So to do that, we constructed a function like this, which is basically a linear combination of the basis spectra from NV0 and NV minus, and C0B and C minus B are the coefficients which determines the contribution of the signal from NV0 and NV minus to the total PL. Now, by fitting the spectrum measured at a random field with this equation, we can calculate these coefficients C0 and C minus. So this curve shows a specific fitting which was done for the spectrum taken at 170 Gauss. And then we did the same thing for all the other field dependent spectra, and we calculated C0 and C minus and then plotted them with as a function of magnetic field. So here you can see that the CNV0 doesn't change with magnetic field, but CNV minus decays with magnetic field as expected. And then we reach a minima in the CNV minus data, which corresponds to the fully spin max state as it was discussed earlier. Then it shows a slice enhancement with magnetic field, which happens due to a phenomena which is basically the dependence of a singlet to triplet state transition in the excited state of the NV on magnetic field, which is discussed in more detail in this paper. Now, since we have the CNV0 and CNV minus, it is straightforward to calculate the function f from these coefficients using the earlier equations we discussed about. And now, since C0B1 and C0B2 doesn't have the same value and it's applicable for each values of B1 and B2, we can just exclude these terms, and this equation then reduces to this form. From there, we can see how the parameter f varies as a function of the variation of magnetic field, and this is shown in this plot. So a less value of f signifies a large change in the NP minus fluorescence. So to do the spectral decomposition analysis with highest efficiency, we should choose the value of f to be minimum. So in our case, we can see that the square box represents the value of f which we used in our analysis, which is very close to the minimum value of f we could get from in this field range. Also, we can see that the value of f basically changes for a same amount of variation of magnetic field depending on the initial field. So one should be constrained to the minimum starting field, minimum lower field B1 to get the minimum value of f. Next, we applied this spectral decomposition analysis to perform the imaging for NV0 and NV minus centers. So we capture image at 170 Gauss and then capture another image at 975 Gauss. And then we can write this image at 170 Gauss as an addition of the component signal from NV0 and NV minus. Here we consider that under 532 green excitation, there is no other fluorescent center which contributes to the fluorescent. Now, since with magnetic field NV0 fluorescent doesn't change, what I difference gives us is only the change in the NV minus fluorescence. So we use the value of F, which is 6.2, which we obtained from the earlier analysis here, and then calculate the mapping image. We do this operation pixel by pixel and then construct the image INV minus and INV0, which are basically the mapping image for NV0 and NV minus centers. Now here we are assuming that F is equal to 6.2 doesn't change over the sample. That means NV0 and NV minus population ratio is constant over the sample, but which cannot be the case in all samples. For example, mainly the HP-HT grown ones. So in that case, one needs to do the spectral decomposition analysis at different parts of the sample and then determine F in terms of F function of XY, and then incorporate that value of F into this analysis and then get the correct mapping. Okay, so now we show a optical filter-based decomposition analysis. Here we use a 645 nanometer long pass filter, which basically modulates the NV0 and NV minus signal in different ways. So since the NV0 and NV minus spectrum are in different spectral regimes, these filters transmit the NV0 and NV minus center with different fractions. So here is the filter function which was procured from Thor Labs. And now when we modulate the NV0 and NV minus spectrum, it looks like this. The thin blue line is the spectrum and the thick line is the filter transmitted signal, the same for the NV minus. And then when we take the integrated area, ratio of the integrated area under this filter transmitted curve to the curve which was not modulated, then we can get the transmittivity of the NV0 and NV minus center through this filter, which is shown here. And when we have the values of T0 and T minus, we can use that in this analysis to perform the filter-based deconvolution. So here we have an image which was captured without the filter. Then we write it in terms of NV0 and NV minus mapping. Then we include the filter. And now since the filter modulates the signal from NV0 and NV minus in a different way, we write it MLPF, where T0 times NV0 mapping and T minus time NV minus mapping. Now by simply solving these two solutions, these two equations, we can get the solution where NV0 map and NV minus map is expressed in terms of all the known parameters. So when we do this operation for each pixel, we can basically construct the image for NV0 and NV minus, which is shown here. We wanted to check whether this method is efficient or not. So what we did, we simulated the images for NV0 and NV minus. So in this letter NV0, all the pixels are assigned to the integrated signal of the NV0 spectrum, and the same for the NV minus. Then we assume that we place the filter. So instead of PL NV0, we now modify the counts for the each pixel by T0 into PL NV0 and T minus into PL NV minus for the NV minus center. So this is now the simulation for the image, like we have a filter now in front of the detector. Now when we use the same analysis, use the same equations, we can basically separate out the NV0 and NV minus image with full efficiency. We assigned zero values to some of the pixels, and they still remain zero in the newly constructed image. Okay, so in conclusion, we have demonstrated two novel techniques, a spectral decomposition technique to decompose the spectrum and PL mapping image for NV0 and NV- centers. And also we have demonstrated a filter-based deconvolution protocol to separate out the PL imaging from NV0 and NV-. And a spectral decomposition technique is based on the response of the PL signal from NV- charge state under the influence of magnetic field, whereas NV0 center doesn't show any observable change in PL as a function of the magnetic field. So this is a general analysis. It could be applied for any sample, and one has to just choose the filter and take into account the spectrum and calculate the transmittivities. Then it can be applied for other defect centers as well. And yeah, so basically, this method has the flexibility to decompose a PL map also, which is composed of spectrum of different origins and create PL mapping images for them. Okay, so just a word about QTech. This is where we are working, and it has different divisions: qubit research, quantum internet. I'm associated with the quantum internet division and quantum computing. This is a collaboration between TU Delft and TNO. So if you are interested in working QTech, you can go through their website and send applications. And this is the city of Delft. It's a beautiful city with nice streets and canals, and also the Delft blue. So I think that's it.
Okay, thank you, Tanmay. Thank you. Maybe we have a couple of minutes for questions. Tanmay, can you stop your presentation? Then you will see that there is a chat box in which people might have to.
Yeah, okay.
Writing. So there are no questions. Okay. So let's see. Anyone who wants to ask any question can unmute and ask.
Yeah, since others are not asking, can I ask one question?
Yeah, Prashant.
Yeah. See, Tanmay, there was this paper either in Science or Nature about evidence of quantum Darwinism. You know, evidence for quantum Darwinism.
I haven't looked into it. But it will be really interesting to see it. So, from which group is it? Maybe I will have a look into it.
I really don't remember, but I remember it is either a science paper or nature paper last year.
Okay.
So one can check it out. It is, you know.
Yeah, I will look into it and then maybe I'll write to you. That will be great.
Okay.
Okay. So thank you, Tanmay. Thank you very much for a wonderful talk. And yeah, we will continue to interact. Maybe we can do the same technique. So this decomposition technique can be employed in our labs also. So yeah, visit us sometime when you are coming. Now, though, it is difficult for Indians to visit. So
yeah, now, yeah, but
you know, send us your papers.
Yeah, send us the papers. Yes.
I will surely send. Okay.
So have you published anything from that Belgium work yet? Deposition.
Yeah, one paper we have in the line, it's almost accepted, and another we are working on.
Not yet in archive.
Yeah.
Okay. Okay, thank you, Tanmay.
Thank you very much. Yeah.
So Chiranjeev, I'm just
Yeah, so Professor Vedral is there. So
just to say hello to Professor Vedral. Then I'll decouple.
Hello.
Hi.
Thank you for having me as a speaker.
Yeah, sure.
Welcome. Yeah.
We have had long interactions with you. We did experiments on your theory.
I'm very happy about it. I think it's a very exciting field as well.
Yes. So maybe I should start by introducing you. So, are you ready for the?
Shall I try to share my screen?
Yeah.
Maybe.
Share the screen. Let me
to make sure that you can see everything I do. If I bring it up like that, is it visible?
Yes, perfect. This is perfect.
Excellent.
Perfect.
Excellent.
Okay. So, so let us start. So, we are very honored to have Professor Vlatko Vedral visiting us today online, of course. And he has had an illustrious career, and he has been very prolific in publishing in this field. So Professor Vedral did his PhD from Imperial College London under Sir Peter Knight, and after finishing his PhD, he went to do his postdoc in he was there in Oxford University, and then he was a fellow of Morton College. Then Professor Vedral went to Leeds University. So he joined Imperial College as a faculty there, and then he went to Leeds University. And after Leeds University, he came back to Oxford University, and where he is now continuing as a professor at the University of Oxford. And he's also a professor. He has a joint appointment as Center for Quantum Technology at the National University of Singapore. And he was appointed a fellow of Wolfson College in Oxford since 2019. He is also the recipient of Wolfson Royal Society Top-Up Fellowship. So he has published a lot of books, and I'm very proud to say that I own all of his books. So the first one is Modern Foundations of Quantum Optics, then Introduction to Quantum Information Science. This is a book which I've used in my teaching also. Then Introduction to Quantum Physics and Relativity, then Solid State Quantum Information, then Decoding Reality. This is a popular science book, Decoding Reality, the Universe as Quantum Information, and From Micro to Macro, Adventures of a Wandering Physicist. So it's an honor to have Professor Vedral. We have been following his work very closely here at IISER Kolkata, and I have published some work based on his theoretical work. So over to Professor Vedral, and he's going to talk on macroscopic entanglement.
Thank you very much. Actually, the honor is all mine. I'm really delighted to speak to you about the latest research developments. I will probably zoom out a little bit in the sense that I want to say a few words about conceptual issues before I tell you about maybe the latest state of art and the experiments that we are planning. This fundamental side, I think, is captured nicely with this subtitle that I have, which hopefully you will understand what I mean by that, where I say that unobserved outcomes can affect future measurements. I think if there is anything that confuses people or maybe worries people in quantum mechanics at the macroscopic level, if we really are trying to apply quantum mechanics to everything, then it's this aspect that can be put in many different words, but one of them is the phrase that I chose. Of course, the whole field of reference frames and observers and all sorts of other investigations are simply related to this fact. So let me just very briefly go through this. As you know, the whole point of the difference between quantum and classical physics is the notion of quantum superposition. And when you extrapolate that to many systems, of course, this is the notion of entanglement. And the key issue, as you know, I'm probably showing you the favorite interferometer in the field, but as we know, all quantum objects behave this way. Here you have a single photon that goes through a beam splitter. And then, of course, we know that this really leads to a superposition of states that come out in two different ports of the beam splitter. Now, of course, if you detect after that, then you will just get random statistics where each of the detectors will somehow be firing half of the times if you repeat this experiment many times, but we won't be able to predict which of them will fire at each experiment. In order to demonstrate that this really is due to the quantum superposition, it's not enough, of course, to detect. What we need to do is recombine the two possibilities and then put another beam splitter and then ask the question, which way does the photon go now? And as we know, in a perfect interferometer, if everything is aligned properly, then obviously, whenever you send a single photon in, you will only get one of the detectors to click. The probability for this one detection will go to 100%, and the probability for the other detection will exactly cancel out. The amplitudes will cancel out, and they will give you zero probability. And that's really all there is to these, this notion of a superposition. And whenever we discuss which path is taken by this photon, we're somehow forced to acknowledge that the photon exists in both of these paths, even though when we try to detect it directly, we can never really get both of these clicks at the same time in the same experiment. And somehow this captures both of these fundamental randomness or unpredictability, if you like, of quantum mechanics, as well as the fact that if you re-interfere the possibilities, they will actually add up at the level of amplitudes and not at the levels of probability. Now, before I now go into the entanglement side of things, I want to actually say a few words about this, which I think are also a misconception in the field. I want to, and of course, this faces immediately people who think about macroscopicity and applying quantum mechanics, for instance, to gravity. Then you will frequently hear people say, oh, but gravitational field is a local field, just like any other classical field. And then you hear people say, however, quantum mechanics is non-local. And I just want to say that one has to be very careful here, because the non-locality that Bell had in mind is not the non-locality that would exist in field theory, and it doesn't exist actually. Fields, even quantum fields, are completely local. So I want to spend a few slides just discussing this issue. So usually when you talk about a pair of entangled spins, if you like, then what Bell's inequalities or Bell's logic, if you like, Bell's argument really tell us is that we cannot maintain classical reality at the same time as the notion of locality. That's all that Bell says. Bell says, if you manage to violate my inequalities, then you've got to lose either the notion of locality or you lose the notion of reality. And I would say most of us actually in the field, although by no means all researchers, but I think majority of us would say that what the violation of Bell's inequalities implies is that the reality is not composed of classical numbers, as it would be the case in classical physics or classical field theory. But simply what this means is that we should be upgrading our notion of reality, and we are keeping locality. I think that that's the idea. Locality can be maintained, but what cannot be maintained is that reality is described by C numbers. And of course, we all know that the main element of reality, if you like, in quantum mechanics is the operator, is a Hermitian operator, which is basically what constitutes an observable in quantum mechanics. And if you're happy to give up C numbers and only talk about Q numbers, then there is absolutely no problem with locality, and quantum field theory works perfectly well. And I just want to go through this interferometer to show you actually how this is done, in case you've never seen this before. And it will again alert you to why some people think that there is something non-local in quantum mechanics, whereas if you think in terms of operators, you will realize that there is nothing non-local really. No more non-local than any other field theory, which of course can always be made to be local. So here is again a single particle going through an interferometer, and this piece of glass here kicks in a phase, which, as you know, then affects, after the second beam splitter, the probabilities to observe the particle, and they go as sine squared of this phase and cos squared of the phase. Now, if you write this state down here as an entangled state, so this is written in the field theory language, 0 stands for the empty mode. What this state here says is that either the photon is in one arm and it's not in the other, or it's vice versa. And now you see, when you kick in the phase in one of these arms of the interferometer where the photon is, the Schrödinger picture, when you're thinking about the Schrödinger state, seems to imply that we cannot tell where the phase is kicked in. And this is what some people would think of when they say it's non-local, in the sense that kicking in the phase in one arm is mathematically speaking, not physically, but mathematically speaking, equivalent to kicking the phase in the other arm of the interferometer. And suddenly people say, well, wait a second, if I have a superposed photon here, which I'm arguing is equivalent to an entangled state in the second quantized form, and if I kick in a phase, then the formalism doesn't tell me that the phase is kicked in the upper arm and not in the lower arm. The state itself doesn't tell me anything about it. And this is completely true. The Schrödinger state does not tell you this information. But what does tell you the information is the operator picture, the Heisenberg picture. And I don't want to bore you too much with all of these details, but if you were to write the electric field in one of these arms, the left arm, and the electric field in the right arm, this is the superposition, if you like, the state after the first beam splitter. Then when you kick in the phase, it's clear that the phase is only kicked on the left and not on the right. So the Heisenberg formalism, if you follow operators instead of following states, will make no mistake here. It's clear that the phase only exists in one of these arms. There's no non-locality at all. It exists exactly where you applied it. And then you can do the other beam splitter and so on and conclude the very simple, it's just a very simple calculation. Of course, it gives you exactly the same cos squared and sine squared probabilities. But the phase ends up in both arms of the interferometer only after the second beam splitter. Only at the output, when the two arms have actually interacted, does the phase get imprinted in both of the output arms. And therefore, when we detect, we can uncover the phase either through detector 1 or detector 2. And of course, the sum of these probabilities is simply identity. So basically, if you apply the field theory picture, then anything that people would call non-local in quantum mechanics is in fact not non-local at all. It's as local as anything in field theory. And indeed, quantum field theory, one of the axioms, if you like, one of the properties of quantum fields is what field theorists would call microcausality. So it's all about locality, really, and quantum fields are certainly constructed in a way to be local. And if you want to read a bit more, I'm alerting you maybe here to a paper by Chiara Maletto and myself, where we in fact apply this logic even to the Aharonov-Bohm phase. And of course, Aharonov-Bohm interferometer is just one particular instance of the interference that we've been describing. And even there, you will frequently hear that this phase, the AB phase, is non-local. And in fact, if you treat this with quantum field theory, what I'm saying is that this is as local as anything else. So I just wanted to clear up this misconception that quantum mechanics is not non-local in the standard, in the Einstein sense of the word. It is non-local in the Bell sense, but Bell non-locality is a different kind of non-locality. It's just this dichotomy that we have to choose between quantum or classical reality, if you like, and locality. And like I said, most of us choose to keep locality and to abandon the classical reality. So we don't think that the world is described by numbers. It really is described by quantum operators. And now I'm ready maybe to tell you about this aspect that Schrödinger found, of course, fascinating. I think initially he presented it in this paper, probably almost as a paradox. Whereas ultimately, I think towards the end of his life, he in fact changed his mind. And I think he very strongly argued for macroscopic quantum mechanics. I think he would have argued more or less for what I will present here, if I understand correctly various historical accounts that I've read of these things. So Schrödinger told us about when you have two particles, that the states of these particles can be such that you cannot write them as the state of one particle tensor product, if you like, the state of the other particle. They are somehow intertwined in a way that they are inseparable. And of course, this is the famous entanglement. Now, what Schrödinger applied this to, and I think initially, like I said, he thought this would be absurd, but actually finally he conceded that this must be this way if quantum mechanics holds at this level. Of course, that's a big if. We haven't tested quantum mechanics, and I will make a few comments about how far we've gone and what we would like to do, but we are nowhere near testing, of course, superpositions at the level of living beings of this kind. So here is a snow cat, if you like. Here is an alive cat. Here is a dead cat that my students made at one of the winter conferences in Les Houches in France. And what Schrödinger said is, if you have a microscopic system, like a photon or an atom in an interferometer, and if by some chance that microscopic system can couple to the macroscopic system, and this could be done in various ways. He envisaged a bottle of poison that's sitting in one of the arms of the interferometer, and then this poison the bottle gets broken when the system is in that arm, and in the other arm there is nothing happening. And then Schrödinger said, well, look, this has got, according to quantum mechanics, to happen simultaneously. There is a branch, there is an amplitude for the poison to be released, there is an amplitude for the poison not to be released. If the poison is released, the cat dies. If the poison is not released, the cat is alive. And of course, he dramatized this property of quantum mechanics, that when you spread a superposition across more than one system, you will get these famous entangled states, as he called them. And of course, what we've been debating ever since is, what does this mean? And the very simple, the very direct way of putting this is that these branches are a reality, providing, of course, that you can really ultimately do an experiment which brings them back and interferes them. Like I said, the test of quantum mechanics is always to first create a superposition and then to undo this superposition and interfere various branches. And from the results of interference, you can actually conclude whether something is really quantum mechanical or not. And this is, I'm sorry I'm presenting this as a cartoon, but our discussions, of course, are at the level of thought experiments here. Like I said, we can't really do this experiment. But what is interesting, and I think my colleague David Deutsch has taught a lot about this even in the 70s and 80s, he's written papers on these aspects. What is interesting is that you get this possibility where different observers will have different perspectives on the world. And here, with this slide, I will go back to my subtitle, that even the unobserved outcomes may affect future measurements. It sounds almost like a paradox. How can something you did not observe ever affect the future? But that's exactly what entanglement tells you reality is all about. Providing, like I said, it holds, quantum mechanics holds at this level. We don't know that, but one day I hope we will know, actually. So what people like David and many other people, in fact, there are many places where you can read about it, I've written about it recently as well, has said is, imagine you have an observer inside with a cat. If quantum mechanics really applies to the whole experiment, then there will be a branch of the experiment in which Bob, the observer, will be very happy because he sees that the cat is alive and well. And there will be a branch in which, so there is an amplitude quantum mechanically, for Bob to be very unhappy because he sees that the cat is dead. And so actually already now, when one single observer gets entangled to this, you get two different perspectives in which they actually conclude different things. And that's what's interesting. And in fact, and of course, this is where the difficulty is, if you have yet another outside observer, Alice, she will have her own perspective, according to which the whole state of this experiment is still in a superposition. She's not interacted with Bob to end up in one or the other branch. She simply acknowledges that the whole state is a huge entangled state. And there's no contradiction here. This is exactly what quantum mechanics tells you would happen if quantum mechanics is true at this level. Now, why am I choosing Bob here? Why a human? The simple reason is that we can only communicate with humans. If we are ever to discover what this person inside feels like during this experiment, then unfortunately we humans we can't communicate with cats, or most of us, I can't communicate with cats. And so therefore, if you want, of course, otherwise the experiment could even be done with a computer. You don't really need an intelligent or even a living system. It could be an ordinary computer. It could be an AI machine, if you like. But like I said, the way we humans have evolved is really to communicate only faithfully to some degree, or most faithfully, with other humans. Now, what is interesting is that Alice has a way of confirming that Bob has made an observation, even though Bob exists in both of these. There are two copies of Bob, if you like. Our language becomes very inefficient at this stage, but there is a branch in which Bob is happy, and there is a branch in which Bob is sad. Now, Alice, without directly interacting, can actually put a piece of paper underneath the door of the laboratory, and she can say, Bob, do you see a definitive state of the cat, of Felix? And what's interesting is that quantum mechanics would suggest that in both branches, Bob would say yes. So note that it's a very subtle experiment. Alice is not asking what it is that you see. If Bob says, I see a dead cat, that's very unfortunate for Alice, because Alice then gets entangled with the whole thing. But we don't want Alice to be entangled, because we want Alice to construct the interference of these two branches, while at the same time being aware of the fact that Bob has made an observation and the state really is a fully entangled state. So what Alice now needs to do, she gets an answer from Bob, and in both branches, Bob says, yes, I see a definitive state. So Bob doesn't say whether it's dead or alive, but in both branches, the answer would be yes. This is a parity check. If you think in terms of quantum computation, it's a simple gate at the level of 2 or 3 qubits. Of course, in this case, this would be a horrendously difficult experiment to do. But in principle, this is what quantum mechanics would be all about at that level. So at the end of the experiment, Alice would now interfere these two possibilities, which is why I say that the Bob in one branch, unless he's aware of the existence of himself in the other branch, seeing the other outcome, would not be able to predict the right outcome of this experiment, unless he was told by Alice that he's really in an entangled state, which is also possible. That's yet another twist in the whole story. All of this it sounds very weird, classically speaking, but fully consistent quantum mechanically. So Alice would now have to interfere the whole thing, which simply means reversing the creation of the superposition. So any interference experiment is simply applying unitary operation to create the superposition, and then applying dagger to undo the superposition, which is what we call interference. And basically, it would be just a more complex version of the Mach-Zehnder interferometer I showed you earlier. And if you simply get one outcome, the initial state, with 100% probability, as you repeat this experiment many times, this would simply confirm to you that Bob was in an entangled state with the cat and with the rest of the apparatus, although both of these branches in which Bob is, give you a definitive reality as far as Bob is concerned. But at the level of Alice, it is a macroscopic entangled state. So all of this is perfectly consistent with quantum mechanics. But like I said, it makes us very uneasy at this level because it forces us to acknowledge that what Bob doesn't see, the Bob in one branch who sees a living cat has to acknowledge, in order to be able to explain the future experiments, has to acknowledge that the reality, has to acknowledge the reality of the other branch in which he sees that the cat is dead. And both of them exist at the same time. And like I said, Alice can do an experiment to actually confirm this. It's very interesting. And in fact, halfway through the experiment, this is this extra twist, if you like, Alice can even say, listen, Bob, I know you say you see a definitive state, but I can now tell you that you're in a highly entangled state. There are two copies of you. One sees one outcome and the other one sees the other outcome. And she can write this on a piece of paper and communicate it back to Bob. So now both of these Bobs, even though they're in a superposed, in an entangled state, they're actually fully aware of the fact that the other copy, the other reality, the other amplitude, if you like, whichever language you want to use, exists simultaneously. And there's no contradiction here. It simply is what quantum mechanics tells us. And so here is my kind of artist's impression of Alice telling Bob through this laboratory door without getting entangled herself to either of these two outcomes, telling Bob what the state of affairs really is. And now, interestingly enough, like I said, this is a parity check operation. Quantum mechanically, the whole experiment, as far as the logic of the experiment is concerned, could really be done with 3 qubits. There could be one qubit that's in a superposition. There could be another qubit representing Bob that gets entangled to that qubit. And there is a third qubit representing Alice that sits outside of the whole thing and controls the whole experiment. And at that level, you are simply doing a conditional parity check. It's a very simple quantum computation to do to demonstrate this. And no one doubts, of course, that this would work this way at the level of 3 qubits. But of course, it's not as exciting as having living systems being directly entangled to inanimate systems. And all I'm saying here, it's interesting that logically, if you're familiar with this riddle where you come across two brothers who are basically standing in front of two doors, and one of these doors leads you to a very happy place and another door leads you to a very sad place, just like in our experiment. And then the riddle says, imagine that one of the brothers always lies and the other one always tells the truth, but you don't know which one is which. Could you ask them a single yes-no question so that the answer would 100% definitively tell you which door is the happy door? So this exactly can be solved classically with a parity check. You have to kind of ask a question that correlates the answers of the two brothers. And the quantum mechanical analog is exactly the experiment that I told you about, which is why it's possible to make a measurement to confirm that the state of Bob and the cat and the photon and everything else is entangled without actually collapsing this state. So you can confirm the state and then you can use it later for interference. None of this is actually a contradiction in quantum mechanics. And it's really just a simple parity check. Of course, the tricky bit is how to do this coherently with larger and larger objects. And that's exactly, I think, where our field is moving, not just through quantum technologies by making larger and larger computers, but also testing the foundational aspects, which I think is what excites physicists like myself. And then, of course, you can extrapolate this to as many observers, and people talk about these different reference frames, nested observers, all sorts of arrangements in which even different spacetimes could be superposed in different ways and so on. I think all of this, if quantum mechanics applies to macroscopic objects at that level, would be a possibility. So here I have the Mad Hatter. I'm continuing with the Alice in Wonderland analogy. So there is Bob, there is Alice doing the experiment, there is Mad Hatter controlling Alice and Bob and everything else. And each of these observers, depending on the state they're in, depending on whether they're entangled to the rest of the experiment or not, would have their own perspectives. And none of this is in contradiction with quantum mechanics. It's beautifully consistent, even though it frequently sounds extremely counterintuitive. And this is, of course, what many of you would call Wigner's friend. I think Wigner talked a lot about observers observing observers and all confirming each other's outcomes in different branches. And this is a little bit how we think of classicality emerging, in some sense, that one outcome gets communicated and gets replicated in a larger and larger system. And at some point, this becomes simply very difficult to undo, at which point you may want to say that a definitive observation has been made. But like I said, if you really think that quantum mechanics applies at every level, then no observation, in principle, is ever definitive. All it takes is time and money, if you like, to be able to superpose and interfere larger and larger objects. And actually, that's the current state of affairs. We don't have a single experiment so far that contradicts quantum mechanics. But of course, we haven't explored it at the highest level. Now, a few more things I want to say in the second half, that what's interesting when you quantize the whole universe, and this is this famous Page-Wouters picture, is that actually, if you think of the universe being in a quantum state, then being in a different universe is very similar to being existing at another time. And this is this very famous Page-Wouters formalism, where actually what they imagined is that the universe is divided, the quantum universe is divided into two different parts. There is the spatial part, which plays the role of a clock, a very big universal clock, if you like, and there are the quantum fields that exist on top of this space. And so now the whole state of the universe, if you like, could be written in a way that you talk about the sum of n different, n is of course a humongous number in this case, but you're talking about the nth state of the system, in this case the quantum fields, being coupled, being correlated, being entangled in this case to the nth state of space, which Page and Wouters called the clock. So basically the whole wave function of the universe, you can envisage in a static way as containing all of these different states of space, which in this case play the role of the clock. And each of these clocks is somehow correlated to different states of quantum fields. And this is a very beautiful picture, again, seemingly paradoxical, but it comes naturally out of this macroscopic entanglement picture of the universe. Now, the last thing I really want to comment on is really to tell you about the state of the art. How far have we really been able to test, and what is it that we would like to test as far as this macroscopic quantumness is really concerned? And I will now switch, if you like, to living systems, in the sense that various people have also doubted in the history of quantum mechanics whether living systems also can be described quantumly. And I think this is a quote almost from Niels Bohr lectures on light and life. I know people usually talk about Schrödinger and his book, What is Life? But the lectures of Bohr are at least 10 to 15 years earlier than Schrodinger's thoughts on this matter. And Bohr, as you know, saw complementarity in all aspects of science, not just in physics. He thought that complementarity is actually a defining property in chemistry as well as in biology. And in these lectures, he speculated in a very interesting way, I think almost certainly wrong, but I think these lectures are highly stimulating to read. Because he almost says that when you experiment on a living system, you will not be able to simultaneously show that it's alive and at the same time probe its chemistry or its quantum mechanical behavior. So he thought that in order to study quantum chemistry at that level, the system that you're going to be studying can actually not be alive. So there was a complementarity between being alive and being quantum. And I think this is almost certainly wrong, actually. And that's kind of the experiments I would like to tell you about, because we are taking very, very, very simple steps in the direction of testing anything of this kind. But I think it's a beautiful direction because it not only teaches us about the applicability of quantum mechanics in the macroscopic domain, but may also teach us about certain quantum processes in chemistry and biology that have actually previously been ignored. So the experiment I want to very briefly comment on is an experiment. Actually, we are continuing with this line of research, and I will show you what we are hoping to do in the relatively near future. But this is an experiment by a colleague of mine, Dave Coles, who actually put a bacterium, a living bacterium, photosynthetic bacterium, in a very small cavity. This is an optical cavity that's a micron in size. These are two highly reflecting mirrors in which you are trying to get light, quantized light, to be strongly coupled to the bacterium. And at the same time, you're injecting, I think he didn't even inject laser light. He actually injected highly incoherent white light, excited the system, waited for the system to relax, and then observed. This is a simple input-output kind of spectroscopy. And what is interesting in these experiments, again, I have lots of details that I don't really want to bore you with, but what is interesting is that he could show that the bacterium was at the same time entangled to light inside the cavity. It was strongly on resonance. To use the language of quantum optics, this was really vacuum Rabi splitting observation of the bacterium being strongly coupled to light. But at the same time, he could show that these bacteria were alive. And the way he showed that is that they were really keeping a dye molecule, which was in the neighborhood injected there. They were keeping this molecule outside of their own boundaries. And you can show that as soon as the bacterium dies, the membrane is no longer capable of protecting itself, if you like. And this dye molecule can simply then be observed to be inside the bacterium. So it's a very simple witness of being dead or alive, if you like. But in this experiment, Dave had a single living bacterium confined to an optical microcavity and strongly coupled to the quantized light inside that cavity. And again, not to bore you too much, the transitions that he was curious about were really the relevant transitions for photosynthesis. These are the bacteria that are claimed to be using quantum mechanics for photosynthesis as well. So they absorb light at a certain wavelength, then this energy cascades inside the bacterium, losing energy. You can see that the wavelength is getting larger and larger until it finally reaches the reaction center, where it triggers an ATP chemical cycle that produces energy for the bacterium to move about and to continue to live. And what Dave observed like I said, is the vacuum Rabi splitting. As he was changing the size of this microcavity, he was bringing various energy levels in and out of resonance with the surrounding quantized electromagnetic field. And it's this vacuum Rabi splitting that actually he was able to observe for different energy levels that I showed you in this experiment. And you can even, again, I don't want to bore you with the details of this, but you can write a very simple Hamiltonian down in which you treat all the dipoles inside the bacterium as one huge quantum harmonic oscillator, and you can treat the quantized electromagnetic field in the cavity as simply another single mode of the quantized electromagnetic field. And when they couple here, this is the usual dipole times the electric field coupling that we all use frequently in quantum optics. And the interesting thing really is that what this vacuum Rabi splitting observation suggests, if this model is correct, of course, is that the ground state of the bacterium and light should really be thought of as a large entangled state in which you have these small n excitations either in the cavity or absorbed by these dipoles inside the bacterium. And it's a really large
Blackstone, can I ask a question?
Of course, of course.
Yeah, so I was just saying, these excitations you mentioned, these are excitons or there are some other particles here?
Yes, I think you are right. You're right. The proper language is that these are really polaritons, if you like. So yes, these are very highly quasi-particles, if you like, because when you excite a transition, so what we are talking about really is about 100 million dipoles within each of these bacteria. So you could think of a single bacterium as a collection of about 100 million dipoles, 100 million two-level systems, which could be in a ground state or excited state. But when you excite this state, of course, what you're exciting is an electron, but the electron is strongly coupled to the vibronic modes as well. And then through your cavity coupling, it gets also strongly coupled with light. So we have, electronic degrees of freedom dressed with vibronic degrees of freedom, and then ultimately dressed with optical degrees of freedom. It's a highly complex state. Of course, the experiment was only measuring the vacuum Rabi splitting, which is why I think we could get away with an extremely simplified model. But I think if you want to model this in all the details, then it's extremely complicated.
Thank you so much.
Great.
Sir, can I ask a question?
Of course.
Sir, in the Hamiltonian of the second term, can you switch to that?
Yes.
Yeah. So in the second part of the Hamiltonian, there will be 4 terms. So 2 terms will on multiplication. So the 2 terms tells that there is a coupling between the optical field and the bacteria. So what other 2 terms tell us?
Very good. It's an excellent question. Actually, this is very important in the current work which I'm using to extend this. I think for all practical purposes here, you can assume that you are off resonance, in fact, and you can calculate, that you are on resonance, and that you can actually ignore the off resonant terms. But I think you're absolutely right that the other 2 terms, the cross terms, I think you are referring to the terms where A couples to B and A dagger couples to B dagger. Under some circumstances, when you are off resonance, this can actually become very important. This experiment, unfortunately, is too crude for us to even decide whether we need to keep these off resonance terms or not. But I will make a comment on how to probe whether this is the right model or whether we should indeed go into the into the rotating wave approximation as we do in the James-Cummings model? So this is an excellent question, actually, and we don't know from this experiment.
Thank you, sir.
Excellent point. In fact, let me go to that now to say, so this slide simply says that we can in fact even calculate, again, providing that this model that I presented is the right model. It's an extremely simple model because it treats the whole bacterium as a single mode of a harmonic oscillator, which is simply a collection of all of these 100 million dipoles or so. And the other harmonic oscillator simply is there to represent the single frequency mode, the one that's relevant for this experiment, but it's a huge oversimplification. However, as a result of this oversimplification, you can actually study the ground state of this model. You can even use some of the entanglement measures that various people have been developing to say how entangled this state is. And in fact, you can plot that, and you can see that as you change the size of this cavity, and as you bring the wavelength of your light closer and closer to resonance with the dipoles of the bacterium, you will actually at some point hit a critical point where the two are comparable to one another. And this is something that many body physicists would call the point of phase transition. It's a quantum phase transition. So it's very interesting to see that all of these concepts from different areas of physics also come into play, where entanglement now becomes a good order parameter, if you like, a good witness of this kind of phase transition. Like I said, of course, it's very difficult from these experiments, from this single observation that Dave made, which is about the size of the vacuum Rabi splitting. You have to make many other assumptions, like the coupling strength, the number of the bacteria. They all come together, which is why we cannot fully with confidence say the exact point at which we were able to be during this experiment. But I think already the results as they are indicate that we have created a significant amount of entanglement between the two. But now I want to address this very nice question about the off-resonant terms in the Hamiltonian. In order to be able to probe this aspect, you would have to do something more than what we did in this experiment. And in fact, these are the experiments we would like to do. Namely, what you would want to do is not only get vacuum Rabi splitting, but you would like to do Rabi flopping. You would like to do a simple NOT gate, if you like, in the quantum computational language, between the two levels. So you would like to drive the system from the ground state to the excited state and back to the ground state, and maybe shine laser exactly of the right frequency corresponding to the splitting in order to be able to observe Rabi flopping. And then this, of course, would tell you with more confidence what kind of Hamiltonian is the right Hamiltonian to describe this. And this would be yet another quantum aspect that was not really probed in this experiment, but as far as I can tell, could in principle be done. Of course, the difficulty, if you want to convince a skeptic, this experiment is not enough, as you know, because the whole thing could really be described even by two classical coupled harmonic oscillators at that level. And I'm pointing you to a very nice paper, actually, a long time ago, which does that for a different system, but basically uses two classical coupled harmonic oscillators. Now, of course, you know, the notion of being on resonance is a classical notion, and it's not surprising that this could be done classically. In order to really be fully convincing that this is quantum, I would say it's not even enough to do a Rabi flopping between the two levels. What you really should be able to do is make measurements on the two subsystems separately. And this really is very difficult because you're talking about a single cavity. Like I said, these degrees of freedom are highly entangled. So it's very hard to see how one could now separate them and make a separate measurement on the bacterium and a separate measurement on the field inside the cavity, so that you could actually do some kind of even Bell inequality as an entanglement witness. Of course, this would be much, much more convincing. And in fact, I want to show you what we have in mind and what we would like to do precisely to address this kind of question. I think this experiment would be fantastic. It's basically doubling what I just showed you, in the sense that what we would like to do is have two microcavities that are separated by what you could call a macroscopic distance. In this case, I said something like roughly 30 centimeters. I think what limits you in this case is the cryogenics. The experiment in this case would initially be done at very low temperature, so not with a living system. But if you do it at a low temperature, you would, of course, eliminate all kinds of sources of noise. And what we want to have is two cavities, and each of them would then contain a single, either organic molecule or even ultimately, hopefully, a living system, if we could scale it all up and do it at room temperature. But the idea is to send again a single photon. It's exactly Schrodinger's cat idea that we discussed in the first part of the talk, where a single photon goes into a superposition after the first beam split, and then it gets absorbed either by one bacterium and not the other one, or vice versa. And of course, if you do this coherently, this is already shows you how difficult this actually would be to do in practice with a high enough degree of fidelity here. So there are many, many difficult experimental questions involved here. But if everything is done to a high degree accuracy, then as you can see already, the state you are hoping to create after absorbing a single photon is excited one system and ground the other one, plus the other way around. So we are basically creating one of those highly entangled Bell states of these two either bacteria ultimately. Like I said, I think what we are planning to do is do this with simple organic molecules first. Even later, if we do it with more complex systems, we would still like to do this with cryogenics and eliminating all sorts of vibronic degrees of freedom. And only ultimately, really, we would repeat and try to repeat this with a living bacterium or two living bacteria in this case. And I think this would be a tremendous thing. Can you really achieve a highly entangled, macroscopically entangled state of two living systems? And again, if all our intuitions are correct at present, then the answer should be yes. In principle, this is what quantum mechanics suggests to us would happen. But indeed, these systems are so complicated that it's not clear whether we will ever actually be able to get there with a high enough degree of fidelity to really confirm afterwards. All of this optics that follows is meant to be there really as an illustration of the kind of experiment we would have to be able to do to actually confirm that these two bacteria are subsequently entangled. And again, it always boils down to some kind of Bell inequality or other. So I think my time is almost up, and like I said, I'm happy to, of course, address any of these questions in a discussion. It's probably better to leave some of these things for a discussion than talk about them in details. But I think the gist of this whole research, and I think this captures beautifully the major trend in the field of quantum information and quantum computation, is this big question of, does quantum physics really apply to everything, to all objects at all scales? Is it a universal description? And of course, if not, then the question is why not? And what is the next theory? Or what is it that goes wrong? And why does it go wrong? What are the principles, if you like, that quantum mechanics could be violating that in fact will somehow survive in the macroscopic domain. And a very, there are books and books written about this, but as far as I can tell, and I'm going to make a very short statement, I don't see a single contradiction between anything else that we know and quantum mechanics. So far it's been boringly consistent, if you like. For those of us hoping that it might fail, maybe, it doesn't seem to be failing at this level. And I don't think we can see clearly a level at which quantum mechanics would really fail. The beautiful picture that we get out of this, which is something I touched upon very briefly, is that a quantum measurement is not a special kind of operation. It fits in very beautifully within unitary quantum mechanics. Quantum measurement is simply entanglement between two physical systems. And I like this because the distinction between the observer and the observed completely vanishes when you think fully macroscopically quantum mechanically. There are no observers. Observers are simply one kind of a physical system that couples to another kind of a physical system. But observers do not have to have any other special property whatsoever in order to be able to create these entangled states. So I think there is a beautiful simplification when you think about quantum mechanics in this universal way. And something else I briefly mentioned is that time also becomes a form of entanglement, if you like. So actually all of these universes at the level of the whole universe, all of these times simply become different branches of this universal state. Of course, we probably will never be able to experiment with the universe at that level. We are part of the universe, so somehow it's difficult to see how we can do interference experiments unless they really take place for free through the natural dynamics of the universe. And these are also interesting questions that various people are exploring. I think the final statement I want to make is that it's a very exciting time for physics, because I think almost for about 60, 70 years, people have been speculating on many of these aspects. They have not been able to make any experiments, any definitive conclusions about it. But I think now we are beginning to address some of these questions. And I think some of them, at least at the simplest level of complexity, will already be answered within the next decade or so. So I think it's a hugely exciting time for physics in general. Thank you very much for your attention.
Thank you very much, Vlatko, for a wonderful talk. Maybe we can take up a few questions. If you can stop presenting, you will see that there is a chat box in which there are some questions.
Shall I?
Yeah, so this is at 7:43, the first question. Why does the phase come in both arms in the Schrodinger picture?
Oh, a very good point. Yes, whenever I give talks of this kind, I'm always worried that I didn't explain, because I'm trying to cover many things, and then each of these aspects I explain very briefly, and I don't manage to explain all the details. The reason is the following one. It's what some people would say, that the global phase of a quantum state is not an observable. You cannot observe a global phase. All you can do is observe a relative phase between different branches. And so the Schrodinger wave function does not tell you where this relative phase is. If you have a superposition, for instance, of two qubit states, 0 plus 1, and if you add a phase, 0 plus e to the I phi 1, then this phase, because of the global phase that you can add of whatever kind, could actually be residing next to the state 0, or it could be residing next to the state 1. And no interference experiment will tell you which of these is the case. So the way to think about this is a little bit like in cryptography, that imagine that you give me a state 0 + 1, and imagine that I kick in a phase, but I don't tell you whether I change it as far as 0 is concerned or as far as 1 is concerned. I give it back to you, and I tell you to tell me how did I kick in the phase, in one arm or the other. You will actually not be able to do that. It's a question that cannot be answered quantum mechanically. My point to emphasize is that the question does make sense physically. It's not that the question is not a good question. It's just that when you only speak about the Schrödinger states and you don't talk about observables, about operators, then you lose this information. But as soon as you talk about the observables, then of course, the observables in one arm of the interferometer will have to change when you put in the phase, while the observables in the other arm of the interferometer will remain the same. And this is exactly what we mean by locality. Actions in one place cannot affect observables in other places in the universe. And in that sense, quantum mechanics is completely local. So I hope this clarifies it a little bit more.
Okay, so the next question is, does superposition in one system lead to entanglement between two subsystems?
Excellent question, excellent. You can almost give a whole mini lecture course on this question. I believe that ultimately superpositions and entanglement are actually the same notion. You just have to be a little bit, so in that sense, you know, both Schrödinger and Feynman were right. You know, if you read Feynman's lectures on physics, he will talk about double slit experiment, and he will say there is only one mystery in physics, in quantum physics, and that's the superposition. And then you read Schrödinger, and Schrödinger says more or less the same thing, but he says entanglement is the mystery. Entanglement is the characteristic trait of quantum mechanics. That's the thing that doesn't exist in classical physics. And actually, I think both of them are right. And both of them are right because the two phenomena are the same phenomenon. Let me just give you a 1 minute footnote on why the two are the same, or when the two are the same. So in order to be able to say that a photon in two different arms of the interferometer is also an entangled state, you have to be able to measure locally each of these arms, and you have to be able to measure not just the presence or the absence of the photon, but you have to be able to measure 0 photon plus minus 1 photon. You have to be able to measure in the complementary basis. And that's the tricky bit. Of course, you know, people can do that. Many experiments have been done along these lines. But so to have entangled states out of superpositions, you first need two different subsystems. In this case, those are the arms of the interferometer. But on top of it, you have to be able to measure two different conjugate observables in each of these. And if you can do that, then I think that superpositions and entanglements are basically one and the same thing. I hope this answers at least a little bit your question.
Maybe I can just add, you had a nice lecture which I saw in YouTube, the slides, where actually superposition can be in one qubit system, and if you take two qubit system, add them up, entanglement here.
Exactly, which is exactly Schrödinger's point, that when you couple a superposition to another system, you get entanglement.
Yeah.
Yes.
So there is a longish question, so maybe you can read it also. So how does nature differentiate between nature of information? We see that Alice getting entangled with any one state of the two superposition of Bob depends on nature of information given Alice by Bob.
Yes, so, I can see it.
Yeah, so let me finish reading. How does nature differentiate between nature of the information such that
Hello?
Yeah, I think Chiranjeev is having some problem. Maybe you can answer that. Yeah.
I can answer if you can hear me. Oh,
Yeah.
excellent, excellent. It's a beautiful question. It is, yes. I think what is crucial, again, this is because of the fact that I covered too many concepts in my lecture. I didn't talk about this, and I'm very happy that you brought it up. It's a beautiful point. I think this is encoded, what kind of information you have is encoded in how the systems couple to one another. And this really depends on the underlying physics. You know, if you have two spins, then of course there will be some kind of spin-spin Heisenberg kind of magnetic interaction, or due to the Pauli exclusion principle as we ultimately understand all of these things. And this kind of exchange interaction will be the dominant way of creating entanglement. In the experiments I was describing, this is of course determined by how we couple to the world ourselves. This seems to me an accident of evolution to some degree. So the fact that we see, so our dominant sense, of course, is the visual apparatus that we have. And in that sense, we simply see the rest of the world optically by absorbing light. And that's the way in which, for instance, Alice could correlate with Bob. It's therefore very important. That's why I said the nature of how Alice asks this question is very important, because by seeing the answer visually, Alice wants to get one kind of information, as you say, but not to get entangled to the two branches in which Bob exists. So this is a little bit like making a global measurement. It's a little bit like, imagine I have a superposition of two different polarizations, horizontal and vertical, of the photon. And now I want to prove to you that this is indeed a superposition of horizontal and vertical, but I don't want to collapse that. I don't want to entangle myself to this. If I make a measurement in the horizontal vertical basis, I will automatically join this superposition, exactly like Schrodinger's cat. But if I take a polarizer and tilt it at 45 degrees, then this photon will always, with 100% certainty, go through it. And this will be my proof that the photon is exactly polarized at 45, which is an equal superposition of horizontal and vertical, but I didn't really collapse the state. And I think that's the equivalent now of what Alice needs to do with Bob and the cat and the rest of the laboratory. Of course, at that level, this is an extremely difficult experiment, because any kind of decoherence that interferes with this information could, in principle, lead to collapse. And this is something you want to avoid. So you want to control the experiment in exactly the way that the only kind of information that gets communicated is the one you engineered, and you don't want any other parts of the environment to be entangling themselves to this. So it's that already tells you why this is an extremely difficult experiment, even with a small living system. Actually, already there, it's extremely difficult. If I may, I'm looking at the subsequent. There is one more question. Please stop me when we run out of time. But I think there is a related question to this question of interference, which is basically why Dirac said that photon interferes with itself. I think this was an early way of interpreting the double slit experiment, which is to say that he was trying to argue that it's not that we have a photon in each slit at the same time, and then they interact to produce the pattern, which would be almost like a classical kind of explanation. But what he wanted to emphasize is that interference is built up from one photon going through two slits at any given time. And that's something that Feynman describes really well. So somehow this phrase seems very confusing to me, but what he means is that there is only one photon really present in the experiment at any time. But I don't know if saying that the photon interferes with itself is the right way of talking about this. I mean, you know, it's really to do with amplitudes for both of these possibilities, and then of course these two amplitudes interfere with one another. Would be maybe a bit more mathematical way of saying that. And the last question I can see is, does the tensor product imply that the subsystems are independent of each other? And I think this is also a very important point. The answer is yes. The tensor product signifies to us that the two systems can be addressed individually and independently from one another. In fact, the fact that we put a tensor product tells us mathematically that they are legitimate subsystems. So what that means is that we can change the state of one of the subsystems without changing the state of the other subsystem. So the tensor product structure is extremely important when we talk about locality. It's exactly the operators in one arm of the interferometer, tensor product, the operators in the other arm of the interferometer. That's the right description. And when you change one of the arms of the interferometer, the tensor product tells you that nothing needs to change in the other arm of the interferometer. I have, please ask me more questions along these lines if I haven't addressed them properly. There is one more question that I said that Cole's experiment, that entanglement is a witness of phase transition. And I think the question correctly asks that what are the different phases in this system? So I think the different phases, when you talk about, that's a very good point, in fact, because in ordinary solid state physics, different phases would correspond to different macroscopic behaviors of your system. So like a liquid and a solid and a gas. In this case, we are discussing quantum phase transitions. It's a more subtle concept. And what this really means is that the ground state of your system is of a very different kind on two different sides of the phase transition. So it's a more microscopic thing rather than having something that necessarily has a macroscopic manifestation. Although what I was emphasizing was this vacuum Rabi splitting. And you could argue that vacuum Rabi splitting is, in fact, an order parameter that is a visible macroscopic manifestation of crossing from left-hand phase, if you like, into the right-hand phase of your system. But I think the language in quantum phase transition has to be different to what we mean by a phase transition, classically speaking. Of course, it's an excellent point. Oh, okay. This is also a very important question, actually. Can we say that the quantum state is not only associated with the object that we describe or observe, but is also an inherent property of the observer? I think what I'm advocating is certainly yes, that if you describe everything quantum mechanically, then you have to assign quantum states to all of the objects that participate in your experiment. And now, one has to be careful, of course, that when you're talking about a bigger and bigger object, this state, of course, will not be a pure state. It's very hard to imagine that we can keep a very large object in a pure state. So you will have to acknowledge, you know, the boundaries between your system and the environment become much harder to define. And when you talk about a large object, then of course you are actually absorbing a lot of the environment into this description. And even then, your state is highly likely to be a very mixed state. And I think when we talked about excitons and then polaritons, you are already going in this direction of combining more and more systems in order to describe a quantum state. But I would say the answer ultimately is yes, you should be able to assign a quantum state to any of the objects in the experiment. And then related to this, how do we represent mathematically two coupled subsystems? Like yes, good point. So once we have the tensor product structure, how do we explain that the systems couple to one another? And of course, we do this through the Hamiltonian. So the fact that they are independent doesn't mean that they are not interacting. It means that if we don't want them to interact, we can do that. And this is why I said we can in principle change the state of one of the systems, but not the other one, and vice versa. That means they are independent. But they could be independent and still coupled to one another, in which case you are not changing the tensor product remains, but what you're doing is you're putting an extra term into your Hamiltonian, which shows that the two systems are now coupled to one another and exchange some kind of information or energy or whatever else, whichever way they couple to one another. So tensor product is just one aspect, and it gives you the freedom to talk about individuality of these subsystems. But actually they could be coupled on top of one another. And that's exactly what I had in this very simple system of two coupled quantum harmonic oscillators. So they were independent in principle, but they were strongly interacting because the systems were on resonance, if you like, in that experiment.
Professor Home has a question.
Yes. So hello.
Hello.
Vlatko, thanks very much for the wonderful talk, stimulating talk. So just a couple of remarks, question. First, related to what you had been remarking now. So when we go from, as your line, from superposition to entanglement, then a fundamental assumption is involved that we are assuming that the Hilbert space of the combined system is the tensor product of the Hilbert spaces of the individual systems. So that is an assumption that we need to go from superposition to entanglement. Would that be the right way of saying that? To
yes, I think
that statement a bit.
Yes, I perfectly agree with you. Actually, that's why it's hard to say that any superposition is automatically entangled unless you can impose
so I think that should be stressed on connecting the remarks between the famous remarks of Schrödinger and Feynman.
That's it. The bunker. Let me use this this moment to actually point out a beautiful paper of yours, which I think really stimulated a lot of the thinking in this direction, which was to do with genetic mutations.
Yes.
That's a beautiful example of Schrödinger's cat, I think, that you have, which I think illustrates these complexities of, as the superposition spreads to a larger and larger object, at which point, if at all, does this become irreversible? So I think that's a beautiful point there. And certainly to call these larger and larger systems entangled and not just superposed, you definitely need to impose this tensor product structure.
So what is your view that recently McConney had a work trying to deduce the tensor product structure from the other postulates of quantum mechanics? So that may be relevant, or is that in this, if one tries to justify going from superposition to entanglement in a logically coherent?
Yes, I don't have a, that's a very nice point as well. I don't have a better way of arguing for the tensor product than simply to say that you are really demonstrating that you can execute all range of transformations on one of these subsystems, while you at the same time show that the state of the other subsystem has not changed. It's interesting to see whether this could be derived more naturally, as you say, because there may be a better argument than why every superposition also has to be entangled.
Yes. I've been wondering about this, so I was very stimulated by your observation. And so what do you think then what is your take on the view that all quantum interactions would necessarily lead to entanglement? Can one say then yes, from the joint in principle? So
yes, I think so. I think the difficulty then, of course, is confirming that that things are entangled. Yeah, can you address them individually? Can you measure? Yes.
Measure them. Otherwise, in principle, they're entangled, like in hydrogen atom.
I would agree with that statement. I would agree with that statement.
So now I like your that. And then, but also there is some observation made that this Feynman-Schrödinger remarks, because you have the commutation relation and the uncertainty principle. So when you say superposition or entanglement is the characteristic of quantum mechanics, so it really does not capture the whole thing. So that should be also qualified.
Yes, I agree. I agree. I fully agree.
Because that is misleading for students sometimes, I think. Because in the derivation of uncertainty, you don't require superposition or entanglement.
Yes, you're absolutely right. I think in physics, we make a number of implicit assumptions that we don't spell out really. So I think you're right. There's so many subtleties there.
Yes, I'm glad to agree. So finally, I must say I was very stimulated by your example that bacteria and entangled. I'll have to study it in more details. But just a query for the moment, you mentioned at some point at the talk about the membrane, the bacterial entering the membrane being quantum.
Yes, so not quantum. Yeah, I think this is, let me clarify that. We wanted to make sure that the bacterium is alive during the experiment, and we didn't know how to conclusively demonstrate this. And I think it's very difficult. You know, even in biology, people argue about the properties of living systems. And my colleague Dave Coles. My idea was more complicated. I thought that they could replicate during the experiment, and then I thought that we could observe a decrease in the intensity due to the increased absorption because there is more and more bacteria. But nice I think idea. A nice idea, but I think it's much more complicated than what Dave then came up with. And he injected this dye molecule, fluorescing dye molecule, which if the bacterium is alive, it's actually keeping the molecule outside. So you can exactly see the fluorescence, and you can see that the dye molecule is separate from the bacterium. But when the bacterium is dead, you can actually see that the two can merge with one another. So it's a very crude biological witness of being alive.
Making distinction between bacteria being dead and alive.
That's it. As simple as that. It's very crude.
Okay, that's a stimulating idea. And I'm glad you mentioned DNA examples. There also the enzyme attachment occurs to the DNA molecule. So there the question of being alive or dead. Okay. It could be very interesting.
I think so.
Thank you, Zlatko.
Thank you very much.
We'll be in touch, and
I'm looking forward to that very much.
Okay.
I have just pasted one of your nature papers, on macroscopic entanglement here, so people can
Thank you.
Yeah.
A very enjoyable talk,
Thank you very much. Very, very much. We'll be in touch. Yeah.
Thank you. Take care. Thank you for inviting me.
Thank you.
Bye-bye. Bye.
Bye. Good night.